Abstract Algebra 1. I'm Imam, a lecturer at the Department of Mathematics, Ahmad Bello University, Zaria. This is Lecture 2, Compound Propositions and Logical Operators. In the last lecture, we saw examples of propositions such as ABU is a polytechnic in Zaria. And then one of the other examples we saw is this one: 6 is an odd number, or 5 is a prime number. So if we can observe these two propositions, we can see that the second proposition here, a true proposition, it is composed of two other propositions. In other words, it can be decomposed into two propositions. 6 is an odd number, can stand as a proposition, and 5 is a prime number, is also another proposition. But then we use some word like or here to connect the two propositions. So it is the case that some propositions can be decomposed into smaller propositions, while some propositions cannot be further decomposed into smaller propositions. Like ABU is a polytechnic in Zaria, it cannot be decomposed into any small proposition. If you try to break the sentence, it is no longer a definition. A proposition is said to be a compound proposition if it has other statement as its component, like this proposition number 2 over here. Otherwise, it is called atomic proposition. We use uppercase letters P, Q, R, S for compound propositions and reserve the lowercase P, Q, R, S for atomic propositions. So this is what we are going to be using always. Whenever we want to refer to a compound proposition, we use uppercase letters to represent them. And then lowercase letters will represent atomic propositions. If a compound proposition P is made up of atomic propositions P1, P2 up to Pn, then we write P equal to P into P1, P2 up to Pn. So we are going to treat the compound proposition as a function of the atomic propositions and call the atomic propositions the primitives of the compound proposition P. So in fact, this is what Boole was suggesting, that we can see compound proposition as being functions of atomic propositions, and then thereby doing some analysis similar to the ones being done with operations of numbers for propositions. Examples of compound propositions. So if we let P to be this proposition, I'm playing tennis, and Q to be the proposition 10 is a prime number, and then R is the proposition the sun is shining. So if you take these three propositions, each one of these three propositions is an atomic proposition. One can formulate a compound proposition using these atomic propositions. So the following are examples of compound proposition made by the use of these atomic propositions. So if you take P, a function of P and Q to be I'm playing tennis, or 10 is a prime number. This is a compound proposition, and it is made up of this smaller atomic proposition I'm playing tennis, and 10 is a prime number. Likewise, if you look at this proposition Q, which is a function now of Q and R, the small q and r here, atomic proposition, if you say if 10 is a prime number, then the sun is shining. This is again a proposition, but it is made up of the two proposition P and Q. So therefore it is a function of the two propositions. So it has Q and R as its primitives. And then you can also say if the sun is shining and I'm playing tennis, then 10 is a prime number. This is also a proposition. It uses all the three P, Q, and R atomic propositions in it, and so therefore it has primitives as P, Q, and R. And then you can also have this atomic proposition, this compound proposition S of P, where it has only one primitive. It is not true that I am playing tennis. You can see it is not true that I'm playing tennis is also a proposition. One proposition as it is constituent, which is P. So P is the only primitive. So this can be seen as function of a single variable, or function of two variables, or a function of three variables. So according to the number of atomic propositions involved in a compound proposition, that proposition can be treated as a function of the number of atomic proposition involved. And those atomic propositions will now be called the primitives of the compound proposition. So if you look at this P, is just this capital P compound proposition, it is P or Q. So we are just taking the two propositions and combining them together using this word or. And this one, it uses the phrase if then. So if Q, then R. And here we have if Q and P, then if R and P, then Q. And this one uses the phrase it is not true that P. So it is like you are asserting that it is not true that the proposition P is true. So these words and phrases that we use to connect or combine primitives to produce a compound propositions are what we call logical operators or logical connectives. We are going to define that. Since each atomic proposition P can be seen as a compound proposition, P of P equal to P, just like the identity mapping. So you can treat an atomic proposition as a compound proposition as well. So we shall simply throughout this course say propositions to mean compound proposition, to mean compound propositions, including atomic propositions. So whenever we say proposition, we are referring to compound proposition, and this should include atomic proposition. So this is what the language we are going to use. So as we saw in the last example, the connectives, the words and phrases we use to combine atomic proposition to form compound proposition are called logical operators or logical connectives. Sometimes we say logical connectives or logical operators. These are just like the operations we perform with numbers. We say addition, subtraction, multiplication of numbers, and this will produce new numbers for us. So if you combine atomic proposition using logical connectives, and these are the phrases we saw in the last slide, like or, and, if, then, it is not true that, all these ones are used to combine atomic propositions to produce a compound proposition, and these are what we call logical connectives. And then some of the basic logical connectives include the ones we saw, like not, and, or, if, then, and if and only if. And these connectives are symbolically denoted by these symbols: negation, conjunction, and this is disjunction, implication, and the biconditional or if and only if. So these are the symbols we use because mathematics uses symbols to analyze issues. So we shall discuss this one by one in the subsequent lectures. The truth values of a proposition P, which has primitives P1 up to Pn, depend solely on the truth value of the primitives. Actually, if you change the truth values of the primitives, you expect the truth value of the compound proposition to be changed because it is dependent on the truth value of the primitives. And so therefore, it means given any set of truth values for the primitives, one can determine the truth value for the compound propositions that is formed using the primitives. So a truth table, it is a table showing all the truth values of a proposition, and by proposition we mean compound proposition, for all possible combination of the truth values of its primitives, P1 to Pn. And this is called truth table. So that is what we call truth table. If you can have a table with all possible combinations of the truth values of the primitives, because each primitives can take value P true or false, the truth value true or false. So according to the number of the primitives, if you have n primitives, then there will be 2 to the power of n different combinations of the truth values for the n primitives, and each combination will produce a truth value for the compound proposition. So if you have a table that shows all the possible outcomes of the truth values of the compound proposition, that table is what we call truth table. And we are going to give a lot of examples using truth tables. We will demonstrate the use of truth table in our next lecture, when we are going to discuss extensively logical connectives. So here I define what we call logical equivalence. Two propositions P and Q, as P is equivalent to Q. So this biconditional, but we use double line arrow and double arrow head with double line instead of the implication. So this is logical instead of equivalence. This is logical equivalence. It's not a biconditional. So we use this symbol here for the logical equivalence. This is what we use for the logical equivalence. And we say two propositions are logically equivalent if their truth tables are identical. So if you have two compound propositions that are formed using the same binary, the same primitives, like for example, if you say P imply Q, and you say not P or Q, you will you see these are different pronouncements of the same using the same primitives, but you use two different operators. The first one use implication, and the second one use negation and conjunction and disjunction. But yet again, when you see, the truth values will always turn out to be the same. So the two will have identical truth tables. So whenever the truth tables are identical for each value, for every corresponding set of truth values for the primitives, then we say the two statements or propositions are logically equivalent. So this is what we refer to as logical equivalence. We are going to demonstrate this in example in our subsequent classes. But our today's class is actually to talk about what a compound proposition is, what truth table is, and this logical equivalence. And then connectives. So I give you here exercise to determine which of the following are compound propositions, indicating the primitives. So you just try to determine which one of the following propositions is a compound proposition. For example, here 2 plus 4 equal to 2 plus 2 is equal to 4. This is clearly not a compound proposition because it's just a single atomic proposition. But if you look at this, if you get 100% on the final exam, then you will get an A. This is a proposition, is a compound proposition because you can break it into two smaller propositions. Yeah, like here you get 100% in the final exam. It is a proposition, and you will you get an A is also a proposition. It can stand as a proposition on its own. So it is like you have two atomic proposition primitives, and these are combined using if-then, that is using the implication operator, which we are going to talk about. It is raining today. To be rich is to be poor. All the other ones, you can look at them and see which one is a compound proposition and try to identify what are the primitives involved in the propositions. So this is the content of today's discussion. In the next lecture, we are going to start properly talking about logical connectives. And these logical connectives, as we have pointed out, connectives that are functions of operations on a single primitive proposition. So some of them are single valued propositions like unary operations, and some of them are binary operations. They combine two propositions to produce another propositions, and then we have higher order operators. We are going to talk about all this in the subsequent classes. Thank you very much for being with us, and don't forget to subscribe so that you can follow the subsequent lectures.